In this video, we're going to start to examine the idea of collisions and objects colliding together. And in order to do that, we need to look at the idea of momentum and how momentum is conserved. And the conservation of momentum allows complex collision problems to be solved without knowing the forces that are involved. We can typically derive information about the average force, but most of the time we will not have that known at the beginning. And so momentum, we need to define this first. And momentum, we're going to give the label of P. And it is a vector, and the momentum of an object of mass m moving with the velocity v is defined as the product of the mass times the velocity. And because it is a vector, it will have the same direction as its velocity, and its units are in kilogram meters per second. Also, because it is a vector, then it will have components. It will have a horizontal component and a y component. We can find those separately by taking the mass times the velocity's x component and the mass times the velocity's y component. So this will apply to two dimensions. We can also relate the momentum to the kinetic energy by the equation that the kinetic energy is the momentum squared divided by 2m. Now, one thing to keep in mind here, this is a scalar quantity. Energy is scalar, so we're just looking at the magnitude of the momentum squared divided by 2 times the mass. If an object has momentum, obviously it can change, or if an object doesn't have momentum, then we give it momentum. There is a change in momentum, and we call that change in momentum the impulse of the object. And so a force must be applied in order to have this impulse. And we can find that force based on the fact that the net force is really the rate of change of the momentum. And so the net force is equal to the change of the momentum over the change in time. This gives us a slightly alternative statement of Newton's second law, and is also valid when forces are not constant. And so a lot of times we had to say that forces were constant in order to use kinematics and Newton's laws, but this allows us to even treat those times when forces aren't constant. When we have a single constant force that acts on an object, we can say that the impulse delivered to that object, which we'll have as the I vector, is the force times the time interval. Keep in mind, since momentum is a vector, the change in momentum is also going to be the vector, and it will have the same units, kilogram meters per second. Similar to the work-energy theorem, we have an impulse-momentum theorem that states that the impulse acting on an object is equal to the change in momentum of that object. So a lot of times we'll say that the force times the time that this change in momentum is happening is equal to that actual change in momentum. So the final velocity times the mass minus the initial velocity times the mass. If the force is not constant, we just use the average force that is applied through this time interval. This idea becomes especially helpful when we're looking at the graph of the force. So say we have this force here where the force is changing at some initial time ti and final time tf. Our force is increasing as we go from ti to about this middle here, and then the force starts to decrease. And so the impulse, the change in momentum, is actually going to be the area underneath this curve. And that's always the case. The area underneath a force versus time curve will give us the impulse or the change in momentum. That can also be found by using the average force times the time interval. We will oftentimes use this equation to help us out and to solve for either the time that it takes to change a particular momentum, or to find the final velocity given an average force and the time that that force is exerted. When considering a collision, the most important factor is the time that it takes. And so basically the time that it takes the person to come to rest. So if we increase the time, that will reduce the force, which in turn reduces the chance of dying in a car crash. So the ways that we do this by using seatbelts and airbags. The graph to the right here displays the typical values of the force, and keep in mind this is times 10 to the 5th newtons, so it's actually quite high in a car crash, and the time here is in milliseconds. So say for a 75 kilogram person traveling at 27 meters per second, so that's about 60 miles per hour, and coming to stop in 1/100th of a second. The force that that person experiences is 2 times 10 to the 5th newtons, which is about 280 Gs. That's the type of acceleration that you would see here. And we know from our examples before, that's definitely fatal right there, and that's way too much that a body can withstand. So in order to change this, we would need to increase the time so that way we decrease the force required to stop. Seatbelts restrain people, so it takes more time for them to stop. The new time with a seatbelt would be about 0.15 seconds, and so that causes a much smaller force. Now it's still pretty big. It's 9.8 thousand newtons, so it's still just under 10,000 newtons. However, it is about 1 order of magnitude below the values for an unprotected collision. Airbags are similar in that airbags increase the time of the collision. It will also absorb some of the energy from the body. It takes some of that energy into the airbag, and it'll spread out the area of contact, which decreases the pressure and helps prevent penetration wounds. So in a car crash, we can increase the time, which in turn decreases the force by using both seatbelts and airbags.